thank you all for being here. This is fabulous, and I love this venue, even if we do have to pay for parking. But anyways, so I have to say that this topic for this whole term and the topic this evening is of particular interest to me because when I sat on the California Coastal Commission, we had a number of desalination facilities come up before the commission. And now that I am just an alternate, I still get to think about the moment where I might be sitting up there and have to make a decision on a desalination facility. And at dinner we were talking about the degree to which the science and the engineering behind desal really comes into play or not in making those kinds of decisions about our water infrastructure. So tonight we have three experts who are going to help us navigate this terrain. First, and I have to say, the individual with the most audacious title is Josh Dickinson. Josh is new to Stanford. He just arrived in January, and he is the Director of Collaboration and Innovation at the Engineering Research Center for Reinventing the Nation's Urban Water Infrastructure. That's all. And so he actually has his office right around the corner from the Center for Ocean Solutions office at Y2E2 at Stanford. And he really focuses on establishing and nurturing the relationships between this engineering research center and their industrial and practitioner partners. So tonight, Josh is going to give us an overview of water in California and in the Monterey Bay region in particular. He will do that having served many years back in Virginia, focused on water reuse at the Water Reuse Association and Research Foundation, and with the benefit of several degrees, an engineering degree, a Bachelor of Science in Engineering, a master's degree in Environmental Science and Policy, and a master's in Business Administration. So he's the guy to ask about the industry that desalination is entrenched in. And then we'll move to Jeff Paduan, who's no stranger to all of us. He, of course, is a professor and chair of the Oceanography Department at the Naval Postgraduate School. And Jeff, who has a distinction of serving on the Ocean Science Trust Science Advisory Team, will talk about his role as an expert there on, and having served on and continuing to serve on the desalination panel for the Southern California Coastal Water Research Project, or SCORP. He'll discuss how agency decision makers use research and advice from experts or not. And so I think in particular it'd be really good to generate some questions for Jeff about his perception of the degree to which the science and engineering that his panel has generated are already being used or not. And then we'll wrap it up with Carol Reeb, who is also no stranger to anyone who's been at Hopkins Marine Station. She's a research associate there in the Block Lab, and she got her PhD in genetics, so she can tell you absolutely everything about the origins of endemic intertidal limpets, and also highly migratory fish. Of course, she's done a lot of work with Barb on tuna, among other species. But as just an avocation, Carol has gotten really involved in exploring issues around desalination brine discharge and has really led the field. I know when I've gone to the Ocean Protection Council meetings and talked to folks there, they have come to me and just said what a delight it is to have someone who's really focused on that end of desalination. So we're really lucky to have everyone on this panel this evening, and of course Carol is going to focus on the environmental impacts of desalination. Each speaker will take about 15 minutes, and it'll maybe look a little funky, but I'm going to stand up at the 15-minute mark just to make sure we have adequate time for questions. And when we do get to the end of the panelists' presentations, we're going to take questions from the graduate students. So this is your evening, graduate students, and make the best of it.
Do I need to talk into the mic for the cameras? So I can't walk. Okay. Thanks, Meg, and Kevin and Brock. Thanks for inviting me. It's a pleasure to be here. So I like being the first speaker up. So you guys are still buzzed. So it's going to be a really awesome presentation. So Meg mentioned my title. Basically, all the professors were asleep, and I just came up with my own title, and so that's why it's pretty kind of cool. But my background at the Water Use Research Foundation, we focus both on recycled water and desal. So I have a desal background as well. Kevin asked that I kind of focus more on water supply in California, so I'll kind of breeze through that a little bit, get into some basics, and then I'll talk a little bit about our Engineering Research Center and what we're doing. So that's kind of what I just said. And as far as California water, some have said it's the most hydrologically altered landmass on the planet. Probably little argument there. We have variable climate throughout the state, so most of the runoff is north of Sacramento, but most of the demand is south. The demand's typically far from the natural source, so the Sierra or wherever. It's a long way from where the population masses are. So we have growing urban population here and other places, and continuing agricultural demands. 1 out of 6 jobs in California is still in agriculture. And this water system uses about 20% of California's electricity, and that's and about 30% of the natural gas. So this is sort of the framework that we're working in. So this is just kind of a basic schematic. So source might be the ocean, it might be riverine systems, it might be groundwater. So basically, you've got to get it somewhere, so you move it, then you treat it, and then it goes in the distribution system, and you can use that for ag or industrial or residential or whatever. So what we can do through wastewater collection and treatment, then we can create another source through recycled water, and that can come back in, or we can discharge it back to whatever source that might be. So this is sort of the generic water use cycle. So I thought I'd just outline, to kind of show the scope of everything, just kind of outline a few of the water projects here in California. So this state water project, largest water project ever, anywhere, sort of, uses anywhere between 3 and 5% of California's total energy demand in a year, and it moves water north to south. Then, where I live in the peninsula, we have good old Hetch Hetchy water. A friend of mine who lives in Sunnyvale is on Hetch Hetchy water, and he spent all this money putting in all these water softeners and everything else, and drinking bottled water. I said, your water comes from up there, you don't need it. So anyway, we pump it across the state that way. There's Colorado River, so this is operated by the Metropolitan Water District in Southern California. Anyway, you can see some more kind of funky pumps, unnatural looking systems. And so when you lay them all on top of each other, that's what it looks like. So that's not the California highway system or anything else. That's what the water transport looks like in California. So how's it look around here? Increasingly grim, I would say. So this blue area here, oh yeah, there it goes. So this is the Carmel River, and through litigation, Carmel River water is going to go from here down to here. So that's about 6,000 or 7,000 acre-feet a year that need to make up locally. Also, the groundwater is being overdrafted, and so that's also going down. So how do you make up this demand area here? There's some new aquifer supply and recharge projects that are going on, so that'll make up some. And this is just kind of a list of projects that are scheduled in Monterey currently. So there's ASR, phase 1 and 2. Phase 1 is already going. Local desal, which we're going to talk about more later on today, through through the Regional Water Pollution Control Agency and the Water Management District. They're looking at groundwater replenishment systems similar to what they have in Orange County. Essentially, you go from wastewater to high purity water back into the groundwater, which you could then pump out later, or expanding the reservoir capacity. So all of this means in California, in Monterey, and other places that we work, that this is a special time for water. And probably not since we saw the Clean Water Act and the EPA in the late 60s and around 1970, have all these things come together where the infrastructure is failing, using outmoded technologies. We've got this population increase. You're seeing ecosystem needs. So can we go to some sort of water reuse or other kind of recharge where we actually can benefit the aquatic species that are local? Climate change impacts, highly variable climate patterns, and just issues of reliability and security. So how can we create a locally sort of grown option for water? And so this was sort of the birth of our Engineering Research Center. We have this crisis or impending crisis. We see the opportunities. There are lots of technologies out there that are either being implemented in other industries or they're being underutilized in our current industry. And so just because you have those two things doesn't mean that you're going to have change, but there is certainly the opportunity for change. So the National Science Foundation funded our Engineering Research Center. Most of the other centers out there are biotech or nanotech, and they're looking at biodegradable medical implants or PV cells or some sort of technology. So most of these other centers are coming up with widgets. Ours is sort of a public good, so we have this failing water infrastructure. So what can we do differently? Let's not just invest money into sort of rehabbing these old systems. Maybe we can do something totally different that would be more sustainable. And so the concept is we're starting at the local level. We're looking for test bed sites, and we've got quite a few ongoing. And then how do you scale that up to into a regional level? So it's not just academic research for the sake of research. This is being ground truth with the practitioners. And it's a collaboration between Stanford, Berkeley, Colorado School of Mines, and New Mexico State. So here are some of the areas we're messing around in. So they call this the Stonehenge diagram. I call it the pants diagram. But here's the since we are an engineering research center, we have to do some engineering. So you see a lot of that in here. So what we're calling smart urban water grids. So how do you go towards more automated systems, using online monitoring, using remote sensing and other things, sort of like the smart energy grid. So we've got this concept of tailored water, and so you might be able to, your recycled water needs might not be the same throughout the year. So sometimes in the year you might need nutrients, sometimes not. So how can you design a system, and we've got one up and running in Colorado, where you can either take the nutrients out or leave them in. You could use it for landscape irrigation, or you could use it for aquifer recharge, let's say. So that's one of the technologies we're piloting. Asset management, I've talked a little bit about that. One of the areas that we're really excited about is energy positive systems, and so how can you use the existing wastewater itself, which has 3 or 4 times the amount of energy that's really embedded in it that's needed to treat it. So how can you use that in sort of an energy positive way? So as an example, East Bay Municipal Utility in Oakland, they actually are importing food waste into their wastewater treatment plant. They've got about 11 megawatts worth of capacity now, and their demand is about 3 or 4, and so they're actually selling power back to PG&E. And so I don't think they're very excited about this prospect, but we certainly are from a wastewater standpoint. And then this, on the right-hand side, we have this area of natural systems. So looking at stream restoration, and I mentioned water reuse for ecosystems, unit process wetlands, aquifer recharge. So actually getting down in there and determining what happens with the microbial population, what happens with the chemical constituents, and also using stormwater. So this is just about as local a source as you can have. So how can we manage stormwater locally and reuse that for beneficial purposes? And so up top here, and I think this is probably the most important thing that we're doing, is this urban systems integration and institutions. So there's a lot of good research and technology out there. So how do you actually get this implemented? And so we're working with city planners and city council folks and decision makers, board members to try and figure out, okay, what does the planning process look like if people are planning out 10, 20, 30 years? How do we get these technologies scaled up and into those processes now? And so we're looking at, so here's the concept of, we've got the projects at the bottom, so this is kind of the fundamental research. And then we engage these industry partners here that they might provide equipment or they might provide a test bed facility. And so we're gradually scaling these up to a larger level. So here you can see here, we're doing a little bit in desal, not a whole lot. Areas of smart water grids is something that we're moving into. And our two case study areas are the Front Range in Denver and the San Francisco Bay Area. And so, well, I should have looked at the animation before I did this. So anyway, this is the concept of scale. So we've got, for instance, Mines Park is a housing complex in Colorado. So we're basically mining their wastewater there. We're doing tailored water and other things, and with the plan to scale that all the way up to the Colorado Front Range. So we're working with the utilities there, same in the Bay Area. Will we make a difference? Others have gone before us and failed, let's say. There was a Kaiser plan for regional wastewater back in the late 60s. It was never adopted. So what makes us better or different? It remains to be seen, but here's what we hope to do. We hope to see energy positive systems in 10 years or more, enhance resource recovery and nutrients and energy itself. Just to increase water supply portfolio. So desal, recycled water, groundwater recharge, all of these things should be on the table and looked at. Improved aquatic ecosystems and urban aesthetics. We're seeing daylighting of streams and what is the impact that has on society. And financially and socially sustainable solutions. So these systems have to hopefully pay for themselves, and the public has to buy into what we're doing and hopefully support them. So with that, this is not an Italian sort of curse word, but it's baby sign language that we use with my son. So thank you.
Okay. Well, thank you, Josh. And what I'm talking about is different. And it's really just a little bit about my experience with this particular phase of our local permitting process, having to do with, in this case, desal discharges. And there's quite a lot that goes on in permitting any kind of discharge or intake in California, as you can well imagine. And I've had just a little bit of experience with that, but since the desal topic is topical, I think it's a good thing to talk about now. I just have the title up here, and does anybody recognize the background picture? Some of you must work next to it all day long. I should have set this up so I could back out. I didn't think I would have this problem. that's a jetty coming in to the top there. This is kind of, you can see the outline of different water temperatures coming in along the side. So here, that's coming out of Alcorn Slough. This is the warm water, in this case, from the discharge of the Moss Landing Power Plant in a thermal image. This is, we'll eventually get around to desal, but it does give you a sense for some other discharges in the area, and you know, a sense for one of the most important aspects that engineers try to create in any discharge, and that's mixing of the effluent with the ambient water. So you can see in the case of Moss Landing, there's a fair bit of mixing. Again, this is buoyant water that's going up. And Mark or Pete in the back probably know remember the numbers. I don't. There are millions of gallons a minute and coming out of there, and it's a huge amount of water. So desal is going to be a little different than that. So that science panels, the title here refers to the science panels. I wanted to say who, in this case, that involves. You can see a handful of people there. It won't make a lot of sense unless you have the context, I guess, of what California does about permitting discharges. And I don't think we want to go too deeply into that, but there are state bodies and there are regional boards. In this case, and the regional boards write the ultimate permits, but they usually have guidance from what's called the ocean plan. The state level water board has that talks a lot about what a thermal discharge they ought to do or ought not to do. And so when the regional board writes a permit to allow someone to discharge into the ocean, they have these guidelines. Surprisingly to me, that anyway, those don't exist in the ocean plan for desalination discharges at this time. And better late than never, the state is trying to create those guidelines so that as this onslaught of applications for desalination facilities continues, there is some sort of protocol to follow and at least some best practices in terms of thinking about good designs and not as good designs, and good locations and poor locations. And so that's the idea. I found the process to be moving pretty quickly because they constituted this panel a few months ago, and then we want the report, of course, at the end of this month. And so there'll be a fairly limited, sort of high-level set of things. I'll mention some of those. But they did get a pretty good smattering of people, in particular Philip Roberts, to show you some of his results. He's really one of the most well-known engineers who's been involved in modeling the discharge, hydrologically, the discharge from dense plumes in this case. Daniel and Judith have backgrounds in chemistry and biology and marine impacts, and they've been following up on some of the things that Carol will talk to us about as well. Scott and I have more physical oceanography backgrounds. So who is this for? I mentioned the California Water Board, the State Water Board. In particular, we are trying to provide this guidance to Dominic, who's a senior level staffer for the Water Board. He supports the board, who are appointed officials who make the ultimate decisions about things. The board, in this case, will ultimately approve language that Dominic and Joanna write that says these are the considerations to go through when you're evaluating an application for a desalination discharge permit. So that's really who it's for, and our part is really informational for Dominic. And after we hand off this background document, there will be a whole series of public meetings and hearings that related to that lead up to this language being adopted. First part that we were involved with last month, or back in December actually, there was a 2-day meeting down in Southern California, and this is just the topics that were covered there. The idea was to educate us on the panel primarily to some of the issues around the desalination discharges, and to give the public an opportunity to raise issues to us, the hopes, I guess, that they might get in the report that we write to the staff. So we heard from some very recent, about some very recent large desalination facilities, for example, in Sydney, Australia, that has just been built recently, as well as hearing from a little bit from our counterpart panel, who is looking at the intake side. And Pete Ramonde from Santa Cruz is on that panel. They just met and had their version of this meeting last Thursday at Moss Landing Marine Labs. So they talked about some of the assumptions they made or had made in their report to Dominic. And there's another set of issues that are involved with the intake, and there may be some questions about that later. But there is at least the advantage of history in the case of the intake. I would argue there's quite a bit of precedent in terms of permitting for power plant intakes, for example, and there have been a lot of studies that have gone into creating that precedent. On the discharge side for desalination plants, there really isn't that precedent. And the second day, we were supposed to think good things and plan our report, which we sort of did. Dominic had, and the water board, through him, have these 4 questions, that they want us to address. And looking at those questions says something about their concerns and what they want to hear about in this regard. And essentially, they're hoping to have these guidelines that will tell sort of the layperson what areas to focus on and where to get appropriate expertise as these applications come up. So they want to know what's the state of the art in modeling a brine discharge. There's been a fair bit of concern about the idea of cumulative impacts, which hasn't been defined all that well, but I think that comes up even from a lot of the recent application pressure in Monterey Bay. There have been several small facilities requested, as well as some larger ones, and so people on a regional scale or a larger scale wonder, do I need to worry about the fact that I have my own desalination plant, and then I also know there are 3 or 4 in my area? Is that a problem? And how should you be monitoring these is a critical question for all these industrial applications. So those are the things that we talked about. One of the first things that we decided to make our life easier is that we didn't have to worry about buoyant discharges like the power plant discharge I've been showing there, because there is existing regulatory framework. That was kind of assumed all along, but this sort of flow chart here just illustrates that. Starting with an application to build something and discharge something, there is a fundamental difference in the behavior in the environment, but if that discharge is buoyant or positively buoyant or negatively buoyant. And there's a lot of history for the positive stuff, right? The warm water, the fresh sewage in the ocean, both of those things rise to the surface. Brine discharges go the other way. And so we need to worry about the other ones. And then we'll need to sort of talk in the report about what are the implications or issues to worry about in different environments, like the open coast versus embayments, and in relation to the discharge itself with regard to where that is in the water. I want to make sure I get just a few examples of these heavy discharges and how that differs from this one. So this is my last reference to the old one. There's all this literature about buoyant plumes, including what is this initial dilution, zone of dilution, the zone of initial dilution, the ZID. You see that referred to over and over again. And just from this picture, that's kind of the location where the mixing hits the surface and starts to move out horizontally. So where that high turbulent area is, and there's some specific language that defines that. But For dense plume, that language doesn't exist. That's really the problem that we have in rationally permitting things in California at the moment. And that dense plume is going to go to the bottom. You see some engineering results or modeling results in the upper plot there from Philip Roberts, who's done a lot of this. There is they know quite a bit about the best way to do these things. The best way is to have a very high velocity jet that's pointed at, I believe it's 60 degrees or 65 degrees, something like that, to the horizontal. That provides for the most mixing if you force that jet into a quiescent or background water. And so now there will be some new definitions of the near field that will have to do with the edge of that initial therapy, roughly here in this result. And so, and this is a view of some of those, what those diffusers look like in terms of building an optimal kind of discharge system. I think that the permitters are going to have a lot of cases where they're not willing to or not planning to build something like this. So there's everything in between the optimal case and kind of the worst case. So they have to. It's not always going to be that clear cut in terms of the behavior. And there's also this this area out here, the environment that is a far field of the initial dilution, but may have some serious effects. And Carol will refer, I think, to some of these a little bit, but just quickly, the critical thing that I'm most worried about as an oceanographer is that we draw attention to the aspects that may have far field implications if you have a poor site design. For example, a flat bottom or something worse than that, a big hole or depression next to this discharge is going to fill up and basically be capped off by relatively dense water. And depending on the difference in density between the plume, this is showing in Corpus Christi Bay, that's sort of brine data from a brine plume. In that system, part of the day, given this, the tidal forcing they have, part of the day time they develop hypoxic conditions on the bottom, and that's simply because of this density plume that's moving out along the bottom. And where the bottom flattens out, the mixing between ambient water and the plume water is not high enough to maintain the oxygen demand. And you can write that in different ways, but essentially there's something you can think of as a biologically thin layer, which simply means the oxygen being supplied by the water above is not at a rate that's high enough to overcome the oxygen being used up by the benthic community. And so if that condition persists, then the benthic community becomes very unhappy after a while. And so we really want to look around these sites to make sure in our monitoring that it's not just the pretty engineering pictures that shows us what's supposed to happen, but there are these potential impacts around the site that could increase the size of the kill area, if you want. And they talk about the ZID as being given up to the process in one sense. So we're not that worried about maintaining the benthic communities within the ZID, but I'm worried about knowing what is the size of that true impact area. Can it be much larger than the ZID? Probably could if you have a bad design. And so we're just charged with writing some of these ideas down so that people who haven't been thinking about them as much have that sort of protocol to go by. And I think that's it.
concerns and uncertainties surrounding the environmental impacts of desalination, and the first one, of course, is energy consumption. I won't spend much time on this at all, except to say that greenhouse gas emissions contribute to ocean acidification, and because desalination requires 6 to 10 times more electricity to deliver water than typically is used, the amount of energy and therefore CO2 emissions could be increased. In the Middle East, there's been a turning towards nuclear power to provide the energy, electricity, and that was up until the Fukushima disaster last year. The next thing is impingement and entrainment. With once-through cooling, there's been a ban this year on trying to reduce the levels of the animals that are brought into cooling plants and essentially boiled to death. In desalination, it's an order of magnitude less water taken in, so it's not as big a deal, but nonetheless, tons of animals can be brought in and essentially crushed because you're using high pressure to force water against the salt gradient. One way to get around this is to go below the photic zone, where there's less primary productivity with this deep sea or deep water desal. In Israel, there's been some projects trying to do this, and they found that it takes 240 meters down to get enough water that's clean enough to overcome the filtration. There is a project in Monterey being proposed. However, what I've seen for the pipe location, it's not deep enough. It's only about 60 to 100 feet down. Anyway, what we don't know very much about the deep sea life, so we don't really know how this would impact. Even a little bit might be detrimental. So we need some science for that. The thing I want to talk about today mostly is the hypersaline brine. It can increase, of course, ambient salinity, but more importantly, it can anchor pollutants to the seafloor. So all those toxic chemicals that are used to clean the filters gets entrained in this brine, and then sunk, as Jeff pointed out, it's a negatively buoyant plume. It can be settled on the seafloor. And not only do the animals have to deal with the salt concentration, and the osmotic stress it entails, but also the chemicals. In terms of impingement and entrainment, I want to go back to that a little bit because in Monterey Bay, it's been called a red tide incubator. And so as you know, red tide often is associated with neurotoxins. So imagine bringing in water contaminated with red tide, filtering out the salt, and you have potable water. Now the effluent brine contains essentially 2x domoic acid. You put that on the seafloor, the animals have to deal with that. We know that invertebrates don't really seem to have too much trouble dealing with the toxicity of domoic acid, at least at 1x. But my concern is, what if it travels up the food chain into our food supply? Or what if it starts to impact sea otters in Monterey Bay? As Jeff pointed out, when you have a layer of brine on the bottom, you reduce the mixing, you increase stratification, you cause hypoxia. And all of this contributes to an alteration of the benthic community. In the ocean is not really that different in terms of its salinity variability. It only ranges, on average, between 31 and 40 parts per thousand. And the Red Sea was once considered the most salty sea, aside from the Dead Sea, which doesn't really have a lot of marine life in it, except for little teeny things. But I just wanted to put on here the Salton Sea and Mono Lake, which are also the result of dewatering through agriculture and other uses. And that has increased the salinity over time. And the animals that live in that are not what they used to be. In fact, there was once an attempt to stock marine fish into the Salton Sea, but as the salinity rose to 49 parts per thousand, they pretty much died out. The only thing, surprisingly, in the Salton Sea, aside from microbes and things, are tilapia, which are freshwater fish, but they also like salt. So they're very urethral-haline tolerant, that species is. But the mackerel and the jacks don't live there anymore. In reverse osmosis desalination from seawater intake, I want to make that clear, the brine produced ranges between 50 and 70 parts per thousand. And I put on this map, or this image, the various desalination plants planned for Monterey Bay or that are currently operating. The Marina Regional Water Project appears not to be going forward, but one never knows here what happens with desal. There are many other projects in the wings waiting if that one doesn't work. Anyway, I want to make a point first off about the Sand City. They use a brackish water intake about 21 parts per thousand. Their discharge is 30 parts per thousand. They use a very inefficient reverse osmosis process of about 30%. Santa Cruz plans to use, in their proposal, wastewater dilution. My question is, why not use wastewater purification as a water source? To bring their salinity down to 40 parts per thousand, they're almost using as much wastewater as they are producing brine. Monterey Bay Aquarium currently operates using seawater desalination, extra seawater dilution from their exhibits, and their discharge is less than 40. But the industry standard is basically, it considers 40 parts per thousand as safe. And my argument is that's the upper limit of common marine life in the sea. It's often assumed that salinity has no impact, no significant biological impact on marine life from brine discharge. And that is perhaps because the modeling in the environmental impact reports only go for the first few moments of discharge. And so when someone says there will be no detectable salinity increase 6 to 8 feet from the pipe, I just say let the thing run a little bit longer. Brock Woodson did a simulation for me and for my presentation at the State Water Board in December, and showed that if we take the same parameters from the Marina Regional Water Project, and let it go for 6 days, we actually have a plume that you can see rocks back and forth with the tide. This assumes a flat bottom, which Monterey Bay has a 1 to 2% slope. And so that might, first off, it'll allow the progression of the brine plume away from the point source over time. But my point is that brine just doesn't disappear. It can actually persist, and it can actually persist in pretty high values. It's up near high 30s to 40 in that area, and it encompasses an area about 2 kilometers as it rocks back and forth. So this is again from a sewage pipe 2 miles offshore, and it comes out as a sewage plume would, not in a high velocity jet. The next thing I'm going to do is show you high velocity jet. And since I'm not a physical oceanographer, I did the next best thing, which was put it in an aquarium. And one of my colleagues in the lab helped me do this. We ran the camera and basically put 50 mils of 60 parts per thousand into a high velocity plume, which comes out probably much faster than what would be applied in real life. But nonetheless, I wanted to show you this zone of initial dilution. And if this were to float and mix to the surface, or go to the surface and mix, it would dilute pretty well, I'm sure. But what happens is it sinks. And it sinks because it's heavier than ambient seawater, and it creates a brine field. Animals caught underneath this have to deal with high salt, high chemical concentrations, and potentially high levels of red tide neurotoxins. This is my concern. I don't know if it's going to happen, but it would be nice to get some science into the discussion here to make sure that it doesn't. At the end, about almost a little less than an hour later, this is what we got. This is essentially, there is a salinity difference, but I couldn't measure it with my handheld, but just calculating, there's a 1/10 increase in the salinity between the green and the upper level, and that's enough to stratify that bottom. And in the ocean, small changes in density drive ocean currents. The ocean's highly stratified, and it's not stratified by 70 parts per thousand versus 35. It's stratified by 1 or 2 or 0.1 or 2 parts per thousand differences. Now the question is whether or not brine can accumulate in a basin, and I think the Persian Gulf gives us, after 60 years of desal, an opportunity to say yes, it can. There's a lot of caveats to this I don't have time to go into, but basically you have lots of desalination plants continuously distributing or discharging high salinity brine over decades, and we have in Dubai now 47 parts per thousand in coastal waters. In Bahrain, they have trouble filtering out the salt because it's so concentrated. Their outflow and intake are right next to each other. And in Kuwait, you get offshore peaks of salinity, 50 parts per thousand. Keep in mind, this is a dry, shallow, arid area with lots of evapotranspiration. There's overpumping of groundwater. There's lots of caveats. And it's also a shallow, enclosed basin. It's pretty much well acknowledged now that enclosed seas are not ideal for desalination. In terms of monitoring Spain has published one of the few studies I've seen showing long-term monitoring, and there's a couple of things I want to point out. First of all, this is a short discharge of 68 parts per thousand into ambient water of 37. So the first thing is it does dilute very quickly, right from the start. But after that, it kind of moves out. And this is several kilometers it's moving out. It just doesn't disappear. They're concerned about this migration of the plume because there's seagrass beds that form the foundation of the ecosystem for their fisheries and other things. So they want to keep the brine less than 38 parts, or 38.8 parts per thousand. So they've set up a monitoring system to do this. And they're trying to, the goal is over time to have an alarm system all set up to this, but right now it's just kind of very rudimentary. Anyway, there's another thing I want to point out. There's a seasonal difference in the mixing rate. So in the wintertime, there's much more mixing than there is in the spring. And here's the seagrass bed. And the reason they're concerned, again, about this is because the potential for cumulative long-term impacts. There's so many desal plants in Spain right next to each other, and Alicante is shown there, that these plumes could potentially combine. Luz Iberg and I at Hopkins did one of the first studies on brine tolerance of hatchlings of squid. Squid in Monterey Bay and in California form a major fishery, and they lay eggs on the sandy seafloor, which is a prime area for brine discharge. So what we did, you can see these little guys that we counted. We essentially exposed them to different salinity brines and looked at hatch rates. And this is actually the result. This result is actually very similar to other people's studies looking at brine toxicity. And that is that they are actually quite tolerant to high salt in the way that they live. They survive. And we only got a significant result at 50 parts per thousand. But I want to point out that I made observational data, collected observational data on behavior, and they're very inactive at 40 parts per thousand, and about a third of them are lying on the bottom. Even though they hatched, they're just lying on the bottom at 45. So when you think about what's really, a problem, I think the problems begin before 40, or potentially, well, we observed it right at 40. So we have a student at CSUMB doing a capstone study on the videos that Lou made to study the ventilation rates of all these animals in these various treatments to see if we can come up with a stress response in terms of the respiration. But sublethal impacts could actually play a long-term role, even though they may not die outright. Over generations and generations, they'll eventually wind down and potentially get replaced with another species that can tolerate this or not. We don't know. So, hopefully I didn't go too fast. What are the uncertainties? The questions are, how will brine behave in Monterey Bay? Who are the vulnerable species? The young life stages are the most vulnerable. They don't have the energy reserves. They're still developing. Anybody who's a geneticist knows that you put something in high salt, their DNA folds up like an accordion. The transcription and replication machinery don't work. They die, they get mutations. It's just not good for them. They become dehydrated. Ironically, we talk about dewatering our rivers. We could actually dehydrate our seas by putting too much salt in these coastal environments. Where are the critical habitats of these vulnerable species? Have we mapped them? Do we even know, when we site our desal plants, do we even know that there's a problem in that area? What about the sublethal effects? Acute exposure studies looking for death at 50% is one way to study whether or not there's an impact. But I'm thinking we should probably be paying attention to the long-term sublethal effects as well. It could change the community. And that could also change the fishery. Squid are a major source of food for Pacific salmon, tunas, lots of animals that we make a living off of here in Monterey Bay. Finally, how will impacts be mitigated? As Jeff pointed out, there are now people paying attention at the state level on how exactly policies can be implemented. The problem is we don't have all our gaps filled with the science. There's still so much we don't know. And then finally, who's going to monitor compliance? Is it going to be the desal companies? Is it going to be the state? Is it going to be the many universities we have around Monterey Bay? We have an opportunity here to train the next generation of marine scientists by creating essentially projects from which that can spin off of this. And I hope at one point we might talk about that. So I'm going to leave you with desalination in Monterey Bay. Here it is today. And this is as of, today when I did the latest scan of what might be coming in the future for proposals. And I'm sure not all of these are going to be built, but there they are. Thank you.
All right, so we're going to actually switch gears a little bit and try to get the panelists up here. Maybe we could just sit over here, maybe even just on this part. Would that work?
Ask your AV guy.
AV guy, is that all right?
Sure.
Okay. Do you need this microphone kind of headed over this direction, or? So, come on up. Let's have a fireside chat. Well, I gotta say that collectively you all gave a pretty grim picture of desalination. So, Josh, I'd like to give you the opportunity to tell us why communities and planners embrace desalination. You've done some studies on desal. You're familiar with the technology and its use from your work in Virginia. So tell us why folks embrace desalination. What's the good side of desalination?
Yeah, I think the point that I hear most frequently is that, especially when you're talking about California and imported water and highly variable climate, there's nothing sort of certain about the water supply. And so for folks that are proponents of desal, they say, this is a highly reliable local source of water. We're in control of our own future. So we build a desal plant. It's not perfect. There are, environmental and energy costs associated with that, but it takes us off Hetch Hetchy water or Colorado River water, and it's a locally sourced water supply that, will be there into the future.
And in your experience, have any of the desalination facilities that you're familiar with, have the proponents gone to the trouble of kind of doing the real cost accounting for all the various, both the benefits and the drawbacks or impacts associated with desal? I know if you've been to the Monterey Bay Aquarium, we have the Real Cost Cafe for eating fish. So you go up there and you order your fish, and the folks behind the counter will tell you, all of the implications of eating that one fish and where it came from. So do we have the information and data to do real cost accounting for a desalination facility and really, reduce it to numbers and perhaps a set of qualitative factors?
I'd say that the majority of the data in some cases are there to do that. I think the folks that are trying to build plants, they use kind of relative cost data. So in Southern California, if you say, well, it's really not that much energy required for desal when you compare it to pumping water over the Tehachapi Mountains and pumping it from the north. So they're saying it's a net zero energy sum for desal in Southern California. So those are the types of arguments you see. It's not sort of, here's everything laid out for you because, well, maybe we don't lay out everything else for all the other water sources, and so it's not a fair comparison. So you see a lot of, in my experience, relative data that make it, or that can make it look appealing, but not sort of the true cost of desal.
Okay. Jeff, a question for you. Serving on this panel, you all were, when exactly were you appointed to the panel?
Well, I was appointed last November, and I think they have had some phone conversations a couple months earlier. I was for the last one.
So you're on a really
like
tight turnaround.
4 or 5 months. It's
Yeah.
not very long.
What's your biggest concern about trying to answer these 4 questions that Dom has posed to your panel?
Well, just leaving out something critical, I think, because we're not, I know I don't have
have the resources to go and exhaustively check everything out. And if we had 40 people on the panel, maybe somebody would be guaranteed to know everything. But I just think that's my concern. But the way it fits in the process, I'm less concerned, because you could do a really, if we tried to be very specific, I think it would get thrown out or work backwards, because we're not writing the language, we're just writing the guide, sort of the areas to be concerned about. So it's broad enough that I think we can do, I hope we can do that pretty well. But I worry about leaving out one of those broad categories. If we assume the ocean was always flat, or there was no far field to this problem, for example, as I said, I think that would be a terrible assumption. And so we're not going to make that one, but there may be another one. So anybody who knows more than us, which is a lot of folks, ought to follow the process through the Water Board. There will be, there's public hearings after this. There's a scoping meeting in end of April, I think. So it's just sort of the beginning of the public process.
And Carol, question for you. Two questions. One is just a technical question. What is the nature of the chemicals that you were referring to that are used for cleaning the filters that become part of the discharge?
They're anti-scalants, chlorine, oftentimes, in reverse osmosis filtration, the pH is usually lower when it's discharged into the ocean or in other waters.
Okay. And in terms of the studies that you've looked at on the Persian Gulf, are there any studies looking at thresholds or regime shifts or indicators of regime shifts there?
Unfortunately, desalination began in the Persian Gulf in 1938. It took off in the 80s because there was a growing population with not enough water. And so the decision to move forward with desalination was based on immediate need and not environmental protection. So there's no baseline studies that could really help you out to compare what has been impacted or lost. There's only in just literally the recent 5 years, I've seen papers coming out of the Persian Gulf showing this coastal salinity rise and the oceanographic models showing the entrainment of higher brine levels compared to just a little bit offshore. And also this circulation pattern around Dubai that circulates and allows discharge brine to sort of stay in Dubai's area. So, no, it's just not there.
Can I add a little bit to that?
Sure.
Because this issue of harmful chemicals is one of these topics that is fundamentally different in the heavy plume case from the light plume. And there are discharge guidelines for copper and all kinds of things that they test for at the end of all of these outfalls. And but in a dense plume case, you can have your water meet the requirements for discharging into the ocean, but you have a sediment-based accumulation mechanism that doesn't exist otherwise. So in that ZID, you can end up building up the copper that's coming out there in a way that doesn't happen with the power plant outfall. And then a big storm might move it one day somewhere that you didn't expect. So that's an example of something that's fundamentally different about these kinds of plants.
All right, I've asked my burning questions, so let's open it up. Questions?
Yes. Okay. This is a question for all three of you. It seems like this brine discharge is a huge environmental hazard. Is there any research on other things you could do with it besides pump it back into the ocean? Is there like potential industrial use, and is that something that people use to really into?
Yes.
Good. I don't know.
Yes, there's. Rachel Carson wrote in 1953, The Sea Around Us, that 1 cubic mile of seawater contains $93 million worth of gold and $8.5 million worth of silver. That was in 1953. I just saw this last week in Science that the world is facing a shortage of gold. There's a gold peak, like peak water, peak oil. We now have peak gold. And not that I want to advocate for that, but there is gold in the water. So, you know, I brought up zero brine discharge or zero liquid discharge many times, and there has been research or sort of beginnings of research in this area. When you're talking about large desalination plants, it's off the table because it's just too large a volume until they can get the efficiency of the transition from salt water to potable water higher. If we can have a recovery of 80 or 95%, then the volume of brine is much smaller. Right now, the recovery rates are about 44. So you have almost 1-to-1. For every gallon of water you produce, you have a gallon of brine. If I can get that down to 1/10 of a gallon of brine, now you can start to consolidate that and maybe use the brine or the salts. There's a tremendous potential in the salts, but it's not viable right now.
Yeah, I've seen some other research too on ZLD technologies. I know the city of Phoenix is looking at, you know, basically if you could minimize the brine, then you could deal with a lot of the issues. And I think one of the difficulties is people are trying to say, hey, is there a market out there for the salts? And so Phoenix is kind of working with the nearby kind of salt provider to see if there's something like that might work. But in my estimation so far, there's just not the market for it.
Eric, you have a question?
Oh, I have a question really about sort of the supply and demand for the future. This isn't just for Monterey Bay, but for desal areas. What's to say that once a desal plant is built, that it'll solve the problems and that we won't need more of the water source in other areas? So if it's built in Monterey Bay, 20 years from now, we need water again. Will we have to go through this process again, or how will? Do you see this sort of impact with like the Persian Gulf? How they build plants, we build them again, more people move to the area, more development in that area. So, do you need more water there? Or?
So before you launch into that, do you need the question repeated? Yes. Okay. Who wants to repeat the question? So it's a question that's rather large. Basically, it's about growth-inducing or potential for growth-inducing impacts of building a desalination facility and then falling into the trap where then you are attracting populations and then have to build another one. You know, are there, in your experience, Josh, have you seen effective mechanisms for kind of cabining that or looking at ways to kind of control for that kind of domino effect?
Yeah, I mean, if you talk to utility managers, the ones that I've talked to anyway, you know, their argument is that it's gross negligence if they don't plan for growth. So their thinking is that, you know, the water doesn't produce the growth. They have to deal with sort of the hand that they're dealt with, and they have to estimate, okay, well, there's going to be X amount of growth, and we have to bring in a certain amount of water supply. I think the long-term planning mechanisms for a lot of folks have improved over the years, and so I think they're able to look out a little bit further now. Will we ever have to stop planning for growth? It's hard to say. I mean, at some point, I would venture a guess that, you know, people shouldn't be probably living and golfing in Palm Springs or Phoenix or something like that. But you know, as long as there's enough water to support people, then there will be.
I did some work with some grad students at CSUMB, mostly as an advisor, but what we all discovered was that since 1987, I believe, Monterey now uses 30% less water than it used to, and we haven't really shrunk in population size. So the thing is, when you have a group of people in Monterey and Santa Cruz too that are eco-intelligent and environmentally aware and actually interested in saving water, you can cause conservation to really step in. Yes, we're going to need more water. My question is, does it have to come from the sea? Recycled water is a way to take the old water, recycle it, and put a certain percentage back into the system. And each year in the Carmel River, we get, currently, we have in Monterey Peninsula 7,500 acre-feet of water we get every year from rain and everywhere else. We take a certain percentage of that and add it back into the system, we could actually grow our water budget over time. I'm really optimistic about the future. I don't think desalination is the only answer. I think it's part of the answer. And I think these other diversified solutions, our diversified water portfolio that's been discussed, you know, all over the state, really, is the way to go. And I think, technology will also allow us to make more efficient use of water. So.
Yes. Yeah. Hi, thank you guys. This has been a great evening. I wanted to follow up on what Carol was just saying. In this area, ag is a huge user of water. And so I'm just wondering, we've talked about desal, which is really energy intensive, and we're not sure about the impacts on the ecology, or we're not sure about the impacts on the population, and it's been a cosmic growth. So I'm just wondering, has ag been at the table? Are we talking about reducing the amount of water that they're using so it's more efficient before we go to these really energy intensive measures?
Meg? That sounds like a question for you.
Well, I don't know. You've been sitting in the room where the stakeholders are present. So, each of you probably has a perspective on that question.
A few recent meetings I've been in, the stakeholders have been desal stakeholders and not, a broader group. So I would only be speculating. If I were an ag person, I would want desal just to separate the two issues completely so that those guys in their houses have their water, we have our water, and meanwhile they'll use it all. So whether or not that's a good solution is a much more of a management and planning discussion than a technical one.
So Josh, in your experience and in your expectations moving forward, you're supposed to be working with stakeholders, industry of all shapes and sizes and stripes. Are you setting your sights on the ag industry as well? And how would you engage them on looking at desalination as an option?
Yeah, we're, primarily focused initially on urban water, but my take is that we should treat the water to the appropriate end use, so we don't need desal or RO water to, irrigate crops in Monterey. We've been doing it with recycled water for a long time, and there's a case history there where it's been successful, it's been safe, and so, there's plenty of cheap water available for ag, I feel, but, if we're going to go to desal or some other high purity option, then let's use it for drinking, and let's make sure we're not using it to wash our cars or irrigate crops.
When you drive down Highway 156 or Highway 101 in summer especially, you can see the sprinklers shooting water into the air, and a certain percentage, I heard it was 30%, is lost by evaporation. In other parts of the world where there's not so much water, Middle East, Spain, they use drip. I think everything costs money. I just handed out a science fair award that I created, Water for Our Future, to a student yesterday who showed that the nitrates from ag industry being discharged into the Salinas River are linked to harmful algae blooms, and as we talked about, harmful algae blooms can clog up a desal plant. So ag needs to work, if we're going to go desal, if they want us to go desal, then there needs to be a discussion between ag and desal here. Because the last thing you want to do is create a water solution that, because of the farming practices, causes it not to be reliable. So, yeah, I think, again, I'm optimistic for the future. I think there's solutions. It's just getting people to discuss them openly and scientifically. Yeah.
It looks like all of the projected plants are for, well, not all of them, are for bigger plants. And I know that there are already some smaller ones happening. So is there any talk about the pros and cons of having many small plants that we might be able to do more with the brine, or the brine might mix more, versus some of these larger ones?
That's part of the equation that I think we'll discuss a little bit in the report, and it's certainly part of the motivation for the question that was up there about cumulative effects. Like, is it better to have one big one, or if I have a lot of small distributed ones, are they truly independent, or is there a cumulative effect? I don't know the answer to that. I think that everything that I know about it is going to replicate in these small places as well. So you have to make the same smart decisions, and you want to be on a sloping bottom and not a flat bottom. So if you've got 20 places defined that are ideal, you might end up choosing less ideal locations more often. But it's certainly possible to do that right. I'm not sure about the cost in building these properly designed diffusers as well. If it's a big industry single point, it probably can be pressure to do that or spend that money, it'll be cost effective for them. But if you're a small city or a small company, then the technology you use may be less limited and less effective. Those are some of the things that come to mind, but I think in principle it's the same idea. There's going to be an impacted area. How big is it? Have you accounted for it properly? And all the effects.
So can I just get a point of clarification on cumulative impacts? When I think of cumulative impacts, I think of the full range of impacts that are operating in the same space and over time, both existing and those that are reasonably foreseeable. Sounds like the way the question was posed to you all was just to look at cumulative impacts of additional desalination facilities.
That was the focus, I think, of that question. But some of these other impacts of build up over time are cumulative, I think, in the way you described. So I hope we're talking about both.
Yeah.
I just want to make a comment. A lot of talk on desalination is centered in Monterey and Santa Cruz about the cost of the water to the people, and no one's put a price on the cost of the ecosystem and how that affects other people who make a living off of it. Bigger desal plants are cheaper to run and operate over time, and that's why you see these bigger ones coming up. Little tiny ones, they are a lot more to build. If you added up how much 10 little ones would cost compared to one big one, the one big one would be very cheap, relatively. And the people who pay the rates would rather have cheap water than expensive. So we're kind of at a crossroads right now where we need to start putting a price on the environment. And how much is it costing the environment? And then those people who are making a living off squid fisheries or halibut or groundfish or tourism who have the calamari festival here, how does that impact their bottom line? And that's not been done in this discussion.
No.
Yeah.
Yeah.
Good. I wanted to roll you into this.
That's all right. The other aspect of your question is a really important one, is that on a large plant, it's very difficult to envision anything besides an open water, basically a pipe. And if you go into the smaller scale, then there are two other technologies that are available. One are called filtration galleries, where water can percolate in and flow out. The other is actually you drill and put an intake structure under the seafloor. And so water will then percolate down. And so that pretty much gets rid of the entrainment and pinching. It doesn't do anything to the brine. Still have to figure out a way to get rid of the brine. There have been some technologies that you refill using filtration galleries and kind of move around. They haven't been super successful, but from the intake and tension point of view, moving small has potential of getting rid of those impacts altogether.
Yeah.
I was just wondering about Monterey in particular. I know that some of the desal plants in Southern California are now off the table because they have the fallback plan to make use of the existing infrastructure of pipes, I think. Do we have a fallback plan if desal is not going to move forward? I mean, there's no on the map showing where the water moves in California. There's nothing from construction on the Carmel River.
Any of you who would like to answer that question?
I don't know.
I think Monterey Peninsula has a fallback plan. I think that we have a recycled water facility in Marina that has a capacity of 33,000 acre feet. We have a storage capacity in Seaside Aquifer of 55,000 acre feet. We have aquifer storage that takes excess water from the Carmel River in winter and puts it in the aquifer. I think the amount of energy, it takes about a third less energy to do recycled wastewater and purify it with the desal RO process, reverse osmosis process. To me, I think that is equally viable and cheaper in the long term than seawater desalination. That doesn't mean we don't do desalination at some point, but if you want to move forward with a backup plan, I think we are poised to take advantage of the Marina wastewater facility and develop desalination on that water.
Yeah.
I have a question. This is for all of you, but Josh, you mentioned in your presentation that I believe you're saying you're competing with other technologies like photovoltaics and widgets and stuff like that to get funding. How do we make water resource conservation and recycling projects interesting or compelling as widgets or these kind of technologies?
So how do we make water infrastructure as sexy as iPhones?
Yeah. Well, a few of the things that I keep hearing are, if there's not a crisis, perhaps we create one. And so that could be compiling data in such a way that makes it, compares the variable rate structures and really looks at, what the risk potential is on the Bay Delta and other places. And others just keep generating more data and information that can sort of influence policy and maybe sort of generate mandates. Nothing works probably as well as a good mandate by the State Water Board or others to kind of move water issues through. So those are kind of my 2 points that are sort of crisis mode and maybe a mandate.
So Josh, not to put you on the spot, but I'm about to.
Okay.
So you guys are just spinning up this big ERC with a great big NSF grant, and you're meant to inform real-time decision-making. Is there any plausible way that the ERC could help inform this statewide effort to develop, a policy on how to examine and evaluate desalination as an alternative to other forms of, ways to generate water supply? Is this something that you guys have contemplated doing in California, or?
Yeah, I think, through our concept of, going through from fundamental technology up through test beds and regional sort of collaboration frameworks, this is the potential to say, okay, well, this starts here and we're able to apply it on a greater scale. And, through the political will in the Bay Area, which is one of our sort of test bed sites, then maybe that's a way to influence policy. And so, the water managers are on board, and that's fine, but, we're hearing that the board members don't necessarily understand a lot of this, and the politicians don't. And so how do you sort of take it the next step above to the people that actually are doing the decision-making and the long-term planning and say, hey, this is broken, and these are some potential systems or processes that we can do to fix it. So that's the concept.
So, and Jeff, I have a question you had a question. Yes, right there.
Yeah, so this has made me a little curious about the permitting process itself. And on land, right, there's like general plans that guide each permit is assessed through that framework, I guess. And I'm wondering, does something like that exist for Monterey Bay, or do you foresee that coming? I mean, do each one of these get permitted as an individual decision, outside of the context of the other ones? Or do they get looked at in mass?
They don't get looked at in masses to the extent that we wish they were, I think. I don't know the complete answer to that. I would just say the regional boards deal with their region, so the head of our board is in San Luis Obispo, so it sort of goes from down there to, I'm not sure where it cuts off before San Francisco, I think. So that part of the state they're very familiar with. I think they have a sort of a regional view of that system. But in the ocean plan that I'm talking about, I wanted to make the point is the plan does not say desalinate the water. So we're really talking about a very narrow part of the plan. It says if you are going to issue a permit to desalinate water or to discharge into the ocean, more specifically, these are the things that you should worry about. And then the regional board will say, you've got to put out 10 moorings a year for 5 years and do this, this, and that. They'll have very specific conditions for the discharge permit. But none of that takes care of what you're asking, which is the general plan aspect.
So I can just respond from my knowledge as a coastal commissioner that we have an entirely reactive process. So an application is put forward for a coastal development permit to build a desalination facility or to install some kind of mechanism for pulling in ocean water. And then the governmental apparatus reacts to that. That's where the regional boards get involved and the coastal commission gets involved. We had a time in California where we were very interested in proactive long-term planning for our basic infrastructure, including water supply and energy. And at least with respect to the Coastal Commission, back in the 70s, a state law was passed, and the commission was asked to develop a plan for siting LNG facilities up and down the coast. Well, eventually that law was rescinded, and we've never seen anything like that again. So right now there is no vehicle by which the Coastal Commission or the State Water Resources Control Board or the regional boards right now can do the kind of planning that you're suggesting. Yes, Pete?
Yeah, so let me tell you, precisely what actually happens because I've been involved in all of this, is there are two permitting agencies that matter. There's a Brazilian permitting agency. There are two. One is the Water Board, and it should be implemented, which is just said through the regional board. The other is the Coastal Commission. So the most recent case we came up with the Poseidon case, which is that state big. It's actually pretty big diesel plant, and it would be co-located with a power plant, and which is one way of bringing the water to our gathering there. And both groups made determinations, but they were completely done in the absence of any sort of regional planning. And they use the problem with diesel right now in this state is that there's no law that gives guidance. With power plants, there's an EPA guidance, and it's through the NPDES permitting process. And what they're trying to do now, this is exactly the reason why they're putting these panels together, to come up with a legal framework for doing evaluations, not only in a specific sense, but actually regional. And both Jeff's group and my group are coming up with models for trying to do these assessments, not just on an ad hoc basis, but more on a regional context. That's the Water Board. The really interesting thing, and one of the things I hope that people start thinking about it, the Coastal Commission's got a completely different permitting process, and so they may be completely out of sync. And that's something that should be coordinated clearly with the state to general permitting.
Well, I wouldn't disagree with that.
But it won't ever happen.
But there have been instances where the two major state agencies have coordinated somewhat in their review process, the California Energy Commission and the California Coastal Commission with respect to coastal power plants. So it's not as if this can never happen. I would say, just to add a little bit more to Pete's answer and description, is that there are at least two other major laws that do provide a legal framework for evaluating desalination facilities. The California Environmental Quality Act, which requires contemplation of all the environmental impacts associated with a significant project of this kind, including cumulative impacts that are not only just projects of same kind, but a full range of impacts, and the California Coastal Act, which actually has some very, very strong policy directives and mandates. So we've got, quite a tool chest here. The question is, do we understand the technology well enough and the impacts of that technology and what the alternatives are well enough to give the kind of consideration that most of us hope for with our coastal ecosystems. This is your opportunity to say one last thing, like if there's something that you would want the students in the room to do or be thinking about or, with respect to desalination, what would it be?
I'll start. I guess I would say that, sort of building off of Carol's point, that especially in an urban environment, we have already the water available to us to sort of accommodate the existing infrastructure and even accommodate growth. And so I'd say as best as we can, look at all our locally sourced options of water, and that includes stormwater, recycled water, desal, everything. I think we'd find that recycled water and stormwater and other kind of local sources will be much cheaper and probably more environmentally sustainable. But I agree with Carol. I think desal should be looked at as part of the option. And
You know, we've got the ability to sort of make our own future. Water's already here.
Well, I don't want to tell you all what to do. I think I would echo that to the sense of becoming educated, because I feel, I mean, having talked to, heard about these recycling options tonight for the first time, a couple of them, I feel fairly ignorant about the range of water options. I mean, so it just seems to me, as a citizen, from the citizen standpoint and the investigative scientist, it's become more educated about the water options. And we're talking about desal protocol and technology tonight, but it seems like the bigger picture is being able to make those trade-offs and understanding it well enough to do that. So become educated.
So I'm an evolutionary geneticist. I look at how life changes through time and try to make predictions of how life will be in the future. That's how I got involved in this, because I saw a problem coming and nobody was talking about the science. I look at desal and I look at the industry and I say it hasn't evolved since the 80s. We're still doing the same old thing, huge amounts of energy, high pressure, against nature reverse osmosis. What is that? That's not even right. Forcing water against the natural gradient. And then producing this insidious brine that we just nonchalantly discharge offshore. I look at this as saying nature desalinates water without any impact. Pelicans drink seawater. They have a little desalination factory in their head. They excrete salt crystals using, among other proteins, aquaporins. Aquaporins and this natural technology, forward osmosis, microbial fuel cell desalination uses significantly less energy, and we could actually use aquaporins like the pelicans do to create salt crystals, which then now you can harvest that. The science, we're kind of stuck with doing the things, if it ain't broke, don't fix it. I think we need to fix it because there's so much technology and science right now we could use to apply to desalination in the ocean, which wouldn't have so much impact. And I think that's where we need to go.
All right, thanks. I think our guests will stick around for a little while. I know there are many of you from the community that didn't get a chance to ask questions, so now might be your chance.
Your practical approach.
Can I get your signature?